So our keynote speaker today is a Google developer expert for Android and for Kotlin. She spoke at the first three Kotlin Confs, the one in San Francisco in 2017, Amsterdam in 2018, and she's totally going to outspeak me at Copenhagen this year in December. She introduced Kotlin to the Android world at Google I/O 2017, along with Jake Wharton, only a couple of months after I started my Kotlin group here. And this is interesting. She made the cover of Runner's World magazine in 2014. She ran all the way from New York City to San Francisco on foot. And as far as we know, she was not being chased by law enforcement. Only a couple times. You know, it's normal to want to run from Trump Tower, after all. So also, she was one of the earliest Kotlin developers in the Android space. She's been creating lots of fun over the years at Pinterest. And don't suspend your enthusiasm. Join me in a round of applause for Christina Lee.
Okay, is this working? Can you hear me? No? Yes? No? Let's see.
You have to make it hot, yeah. I'll turn this one off.
Okay, can you hear me now?
Yes.
Yes, okay. Well, I'm a little bit flustered. I don't think I've ever had that nice of an intro. I don't super duper feel like I deserve it. I have been doing Kotlin for a while, and like Colin said, my name is Christina, and I'm so excited to be here. Before I start, I just wanted to actually take a little bit of a poll. So, how many people consider themselves pretty new to Kotlin? Okay, perfect. And then do we have like people who kind of feel intermediate, like kind of comfortable a little bit? Okay, so a few people. And then how many people are like really confident, they've been around for a while? Come on, toot your own horn. Okay, good. So a little bit less. Perfect. So that gives me an idea. Oh, and then one last question. How many people are using Kotlin on Android? Okay, and then people back-end or okay, and then I don't know yet. Nobody. Okay, perfect. That'll help me calibrate as I speak. So with that, we can dive right in. So my name is Christina, as has been said, I guess 4 times at this point, and I'm here to talk about a brief history of the world, and specifically the Kotlin world. I was trying to be at least a little bit on topic to start. Now, the question that I wanted to dive into was, how did we get where we are? I usually give tech talks, and those are pretty focused, and I wanted to take the opportunity to start a conference with a keynote with something that I'm very passionate about, which is actually like more of the meta language discussions. So how did we get where we are? And what's going to drive us to where we want to go next? So in order to start, let's take those questions in order. Let's go with part 1. Where are we right now, or where did we come from? So I'm going to have to throw this back in the time machine. This is actually a typo. That should be 1996. And BK, of course, if you don't speak Christina humor, is before Kotlin. You see what yeah. Thank you. Some people here are morning people just like me. I appreciate you all, every single one of you. Okay, so what happened in 1996? Well, we got Java. And I know that in a community of people who love Kotlin, this can be, maybe an iffy thing to discuss. But Java is actually a really great language. It has some like key principles. It's object-oriented. It built off of what came before it, which was C++ and C predominantly. And there are like many great things about it. It came with like this suite of safety features and this portability focus that people were really excited about back in 1996. But more interesting for us as Kotlin developers is what also came packaged with it, which was the JVM. Now, the JVM has several claims to fame. One of them is garbage collection. At this point in time, if we're in our way back machine in 1996, when the first public release of Java comes out, garbage collection is not exactly mainstream. It was invented back in, I think, 1959, included in Lisp, but mostly people at this time were using C++, which had a manual memory management system. And there are some some good things about doing manual memory management, which is that it's fast, but there are some bad things, which is that like humans are pretty rubbish at a lot of different things, including very seemingly simple tasks, and then you get anything more complicated than this and we're like extra rubbish. And so when Java and the JVM came out and they had this automatic garbage collection that was happening, what we were trading off was this hope for a future with fewer bugs against this like fast optimization and performance of being able to fine-tune things manually. And this was especially true back then, before everything was hyper-optimized. So this was pretty controversial back then. It's still a little controversial now. I mean, Android developers will know that we still write native code for a reason, even though we have Kotlin. But the JVM also had another claim to fame, another thing pushing it towards the mainstream, and that's actually hidden in its name, which is the Java virtual machine. Now, we don't usually say it out that way, but it's very important because the ideology behind having a virtual machine was that we would get this beautiful world where we could write code once and run it everywhere. So if you've ever heard someone talk about the JVM, you'll hear this phrase all the time. This was the guiding vision at this point in time. Now, the way the JVM did that was that it was able to bind itself to a bunch of different platforms like Linux, Mac OS, etc. The ones I've chosen here just happen to be the ones that are supported by the most common JVM implementation maintained by Oracle, which is Hotspot. And what was really cool about this structure was that with a single input, the JVM would be able to take this code and run it on any of these platforms. Now, compare and contrast that to what was happening back then, which was that if you wanted to do this before this, you had to manually write all of these implementations. And so this was pretty groundbreaking and pretty cool. And it begs the question of, great, the JVM's world sounds awesome, but how do I operate within that world? We know that with a single input, we get this vast suite of benefits, but what exactly was that input supposed to be? And it turns out that the people who wrote the JVM decided that the input should come in the format of class files. And class files is just a binary format like any other that specifically happens to be tied to the JVM. And what they contain is bytecode, expectedly, a symbol table, and then a few other little bits of data that you need to make everything work. Now, if you're anything like me, you might be looking at that and saying, the JVM sounds great, but it doesn't sound great enough to be writing bytecode. And I think most people would agree with you. So then, we're building up here. There's the second question of, okay, JVM, great, class files, how do we get something to write class files for us? And of course, this leads us to some more familiar territory, which is Java and the Java compiler, or like more hierarchically, we write in Java, the Java compiler takes that, processes it, outputs these files, these binary format files, and then those can then be used by the JVM. So, this was all a long-winded way of saying that what we wanted back then was the benefits of the JVM, and the way that we decided to get them in 1996 was by using Java. But this black box didn't particularly matter, and it turns out that you can swap it out. So as we progress through history, you saw ports of Ruby for the JVM, ports of Python, Groovy, Scala, Clojure, and then of course, when we fast forward to 2011, Kotlin comes on the scene. Now, this brings us to 0AK, when Kotlin is born. There are very interesting facets around the birth time of Kotlin, though. And the most interesting of all is probably the fact that it was born at JetBrains and driven by JetBrains. Now, the reason this is particularly interesting to us as people who use Kotlin is that JetBrains has hundreds of thousands of lines of Java code, and they did back then at least. So I don't know how this has changed now that they have Kotlin. I'm sure they still have some, though. They also happen to be a company who was in the business of putting out world-class tooling. Anybody who has worked on iOS, I'm sorry, I love iOS, but Xcode, IntelliJ, it's really not like an even playing field. These people know how to make tools, and they're really, really, really good at it. And lastly, they had this strategic advantage, which is that the tools that they were making were at the nexus of a bunch of programming languages. So if you are making IDEs for the most popular programming languages in the world, you are studying the most popular programming languages in the world at all points in times. You know what you need tooling for because the language is weak in that area. You know the types of things you need to warn for, the types of things that will break the build, etc., etc. You have this vast repository of knowledge about all current programming languages at your fingertips in this single company. And when we look at Kotlin, we can directly see these things get mirrored into the language. So for instance, if you are a company looking to build a tool that you want to use and you have 100,000 lines of Java programming language code, you prioritize interoperability. It's non-negotiable. Now, if you're good at tooling, you also do really cool things like the Java to Kotlin conversion tool. This is wild, like when you take a step back and you realize that you can adopt a programming language without ever knowing a single word of it by just clicking a button and having it write the code for you. Now, it doesn't work 100% of the times, but by and large it does compile, and maybe it's not idiomatic, but it's Kotlin. Like, you can adopt this language without knowing the language because the tooling is that good. That's wild. And, of course, you also see this in the language features. Kotlin has most of the best language features from other modern languages, but it borrows heavily from across the board. If you look at the documentation, it obviously throws to C#, but they also even mention that they were inspired by things like JavaScript. And so you're seeing that all come together because of the people who created Kotlin in the first place and the context that they were in when they did that. So that brings us to part 2. Which is, where exactly are we now? And so if we remember, there's like this world of the JVM, and it has this great property where like I can do less work and get more output, and that sounds awesome. But there were already like 6 other languages targeting the JVM. So you have to be particularly motivated to decide that none of those 6 actually work for your case, and you want to write a new one. Because this is not an easy or inexpensive endeavor. And so why did JetBrains feel compelled to do this? What were they in search of when they made this decision at this point in time to pursue a new programming language? And well, one of the things was they wanted something with a stronger type system. They wanted to shore up some issues that they were seeing. Now, you knew this was coming because it's contractually obligated in every talk ever given about Kotlin. And so yes, I'm here to fulfill my contract and mention null pointer exceptions. You can report back to JetBrains, it's done, signed on the line. Okay, so null pointer exceptions. We all have heard talk about this. Like when you were selling this to your boss, you're like, hey, yeah, you don't like these, we don't like these, they're gone now, great. But there's a bigger story around null pointer exceptions. And that's that in order to shore up the null pointer exception problem, what Kotlin did was they kind of like split their type hierarchy. And what that looks like visually is something like this, where in that Java world early on, everything that was an object had the ability to be nullable. That was just a state. And in Kotlin, they decided to mirror these type systems. So you could get things that were non-nullable, those are in the left-hand corner. Those things can only hold an actual object. They can't hold that null reference. I mean, they can, but it'll crash. And then there's this whole other mirrored type hierarchy where everything is nullable. And then these have very defined and predictable relationships between each other. Also, this slide was given to me by Svetlana, who works on the JetBrains team, so credit where credit is due. But beyond shoring up that type system by splitting out that hierarchy and making it explicit, they also added some tooling like the null safe operator, which is just a fancy way of saying a question mark, which I'll give them. Like, it sounds much better when you say a null safe operator than when you say like, hey, this question mark's great. And so together, this like kind of massaging of the type hierarchy and this tooling that helped make it safer to work with really shored up this very common issue that Java developers at the time were facing. Now, it didn't get rid of it. There are still many ways to shoot yourself in the foot. And if you look at them, though, this is where the actual difference is. Not that we could get rid of them totally, but that we could outsource the problem to something that was much more defensible than what it had been previously. So previously, you could just like turn around and run into a null pointer exception, and that's very frightening. It's like a scary movie. They're always in the basement. But in this world, what happened was we were able to push that problem into an area that had very bright blinking lights saying, if you go to this area, it will be dangerous, please do not go. And in a scary movie, this is exactly when they would walk into that area because they never have any common sense. But in our world, in theory, we are smart programmers, and what we would do is we would say, we are not going to use the double bang operator. We are not going to explicitly throw a null pointer exception. And if we take this common sense and apply it, and we listen to our IDE when it tells us that we're going into a dangerous area, we can by and large avoid this problem. So strengthening the type system came about in many different flavors, though. That was the one that most of us talked about, but of course there were other ways in which this work was carried out. So the introduction of invariant arrays to get rid of some runtime problems around typecasting, the removal of some legacy features from Java. For instance, Java didn't start with generics, and so we had these raw types, and then they introduced generics, and then you don't want to use raw types anymore, but legacies are not still there, so we cleaned up some stuff around that, and then we solidified some concepts that until then had been a little hand-wavy. So if you don't know what SAM stands for, it's a single abstract method interface. And what that means is basically, for my Android folks, like an on-click listener, an interface with just one method. And what was happening was that there was some like magic where you could pass a lambda to an interface that only had one method, and then things would happen, and that would be the implementation of the one method. And it works, and we still use that, but it's a lot cooler and a lot more explicit when we can just say, here's a function to run, instead of saying, like, here's a lambda, can you put it inside this function in this abstract method? And so all of these problems you could kind of classify into this fixed category of like, there were some non-controversial issues with Java, like let's just nudge those in the right direction. And nobody's probably going to take you down to the mat and say, I really loved NPEs, I can't believe you took those away from me, I'm out of here. That's not really what you're going to face in this scenario. But that was not true of all the decisions that were being made in Kotlin at the time. So another key language feature was the removal of checked exceptions. And this is a much more controversial decision because a lot of people will equate checked exceptions with safety. And I'll offer my opinion that this is probably actually a pretty safe thing to say. If you force people to handle exceptions, in theory, their code should be a lot safer because they're not like hearing a siren going off and saying like, that's cool, maybe I'll get to it tomorrow. They're like actually supposed to respond to the siren in the form of an exception. And this is like the magical theory. Yeah. You know where this is going. Humans are rubbish at a lot of things. And so in test projects, it was like all fine and great, right? And the exceptions were being caught. And then you went to this production code base where people only have 40 hours and then they want to get out of their workplace. And all of a sudden, you have comments like this one, like, is it actually going to happen? I don't think it's going to happen. So you say, this won't ever happen, and then somehow it happens. It's amazing. It's wild how that happens. And so you would get into this situation where things like console.log, like if you're logging somewhere, that's an I.O., right? Like you need to write it somewhere. And so in theory, that can give an I.O. exception. So basically, every time you want to write something, you should probably be catching that exception, except for that we use logging all the time. And really, do we have time to catch all the exceptions in all the places? No. So you get to this point where this quickly breaks down in a big code base. And so this is a part, I will return to this, this code really quickly, but this is where I want to pause and introduce three things that will be very important going through the rest of this talk. And these are the language design principles. So the first is safety. The second is being concise. And the third is being pragmatic. Together, these three words encompass JetBrains' ideal for what Kotlin as a language should be. So let's return now to this example of a choice that they made in designing the language. They got rid of checked exceptions. Now, if we look at checked exceptions on the safety metric, can argue that this was a bad call. Checked exceptions are safe, and removing them makes us less safe, because now an exception comes up and like maybe we don't handle it and whatever we're doing crashes. But it makes a lot more sense, this decision, when you start to evaluate it on the other language criterias. Checked exceptions are not concise. You get a lot of code where even if you're ignoring them, you still have this 5 lines that you need to wrap it with. And they're certainly not pragmatic, because people in large code bases were by and large just going through the motions and not actually utilizing them in the way that people thought that they would. And so, when you got rid of them in Kotlin, a decision that at first might have seemed, what was happening here makes a lot more sense. And we see this play out repeatedly. For instance, in platform types. And it looked like there were a lot of new people to Kotlin, so if you don't know what platform types are, they occur when Java and Kotlin are communicating with each other. And so the reason that we have these platform types is that in the Java world, you don't have nullability information, or at least you're not forced to. If you add annotations, it's fine, but by and large, a lot of things are unannotated and they're not required. And in the Java world, or in the Kotlin world, everything needs to have nullability information. I need to know its nullability status at all points in times. And you can imagine how then these two things talking to each other would be incredibly problematic, because one needs this information and one doesn't have this information, so what are they supposed to do to bridge that gap? And so what Kotlin decided to do was introduce platform types, and these are types that you can't actually instantiate. The only time you will see a platform type is if there is a crash and you're debugging it, and if you see something that's like T with an exclamation point, that's a platform type. It's not anything that you can actually use in your code. But what they are is they are something that allows you to treat the variable in question as either nullable or not. This is different, of course, from what we have, because normally if something is nullable and you use a null safe operator on it, things are fine, but if you don't, it won't compile. And then in the other direction, if something is not nullable and you use the null safe operator, then you'll get a warning saying this is unnecessary, don't use this. So normally you have to adhere to a pattern of whether it's nullable or not, and if you go in the wrong direction, there will be some warning, be that a compiler error or an IDE warning. In this case, you will get some object, like my fun or my object, and it won't give you any complaints in either direction. You can add the null safe operator, it won't complain. You can leave it off, it won't complain. It's basically the type system equivalent of a Shrugsy emoji. Up to you. How do you feel today, boss? And this was very controversial when people were learning Kotlin. Like, they were looking at this and they were saying, you promised me this world in which NPEs did not exist, and then you put in these platform types and it's totally possible for them to crash because you're just shrugging off your duty to give me information that will keep me safe. And so I know when this came to my company, people actually were asking the JetBrains team, like, why did you make this decision? It doesn't make sense. It doesn't line up with what I know about the language. But again, if we go back to those design principles and we start looking at some real-world cases, like maybe we have something like this, which is not unreasonable. If you assume the safest path, that everything is nullable, then you get into this state where all of your access makes you want to cry at your desk. So, is it concise? Absolutely not. And the problem with that, over the fact that being concise is one of the language design principles, is that it makes interoperability really painful. And remember, this came from a company with hundreds of thousands of lines of Java who really needs it to be interoperable. And if interop is hard, it means that people won't adopt this language. And if people don't adopt the language, that's not very pragmatic. Like, I don't know how you're going to define pragmatic, but I think people not using the language probably doesn't meet that bar. And so, this is how this language ends up with things like the Shrugsy platform types. Like, because when you apply this rubric, something that at first would seem very off-putting or maybe not in line with their ethos actually makes a lot more sense. And it turns out that once you are aware of these design decisions, that this balancing act can be seen everywhere in the language. Like, once you see it, you cannot unsee it. And so there's this hierarchy that features in the language will go through, which is that the ideal state is that you are all three of these principles. And then it kind of gets like, okay, 2 is pretty good. And like, one is better than none, so we'll take it. And then like if you're in the point where you're adding something to the language and it's not safe, pragmatic, or concise, then you probably need to think about your life decisions. I mean, maybe there's a reason that you need to do that, but like also just take a look in the mirror really quick. And so like when we run through features, we start seeing these things play out. There are some that really easily meet the bar for all three. Like nobody's arguing about smart casts here. And like data classes are a pretty easy win that don't have to sacrifice anything. But others, like string templates, it starts to get like a little more into that two area, that trade-off, where like I don't know that you can argue that string templates are like super safer than what we were already doing in Java. And then type inference, like really concise and definitely makes us move faster. But if anybody forgot to use like a return type and accidentally set their variable to unit because they didn't explicitly return, then they know that type inference is not exactly like the safest thing that we can do. And then there's null safety, and you can argue the point about whether it's concise, but my point here is that in Java you could ignore null safety and just reference anything, and in Kotlin now you have to propagate all of your checks and they're non-negotiable, your program won't run, so like conciseness maybe not as much. And you have extension functions and operator overloads, and then we even get down to the level of like the read and read-write thing. So this is the list versus the mutable list, and the reason I would say that this is not as concise is that in Java you can do whatever you want, but in Kotlin if you have something that's read-only and you want to write to it, you have to start manipulating that data and say like to mutable lists, and then you can use it. And so my point here is that when you go through the features in the language, you start to see this matrix playing out. And most of them are squarely in the center of it, or at least in an overlap very solidly of two different categories. But there is no such thing as a free lunch. I think there's supposed to actually be an I there, like it's Tinstafel. There's an is. There is no such thing. And you know, this plays out as well. So we have this matrix where we're getting all of these cool things and they're safe and concise and pragmatic and we love it. But then if we evaluate how those things are actually getting done, we start to see some things like boxing around primitives. And so the way we get those fun nullability benefits is that instead of using a primitive int, we will have this like auto boxing functionality that will under the hood kind of like box this JVM primitive, and that gives us the ability to represent it as a class, which gives us this ability to have the nullability data, and also gives us these nice things like universal usage APIs, so you never have to wonder like, is this a case where I should use a lowercase I nt or an uppercase I integer, because all of them just seamlessly transition. But this transition is happening because under the surface they're being boxed into a class as opposed to a primitive. And you can understand that the reason primitives are attractive and the reason people were excited about them was that they were cheap and highly optimized. And so this brings us back to where we started, which is like these debates around garbage collection. Now obviously boxed primitives don't rise to quite this level, but it's a very, very similar argument in terms of the fact that it pits this idea of safety versus an idea of performance. So this ease of use, this ability to write the code we want versus how fast this code can run. And the reason that this relationship is very tenuous is that nobody ever tells you like, be careful, speed up, right? Like no. If they're telling you to be careful, it's always like, whoa, 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 be careful, slow down, hold on. Because when you are trying to be careful and when you are trying to be considered, you go slower. You don't speed up and run through life and take extra caution. They're kind of like on these opposite sides in the continuum. And so when you start to evaluate things, like we revisit null safety is not magic. The good thing about the fact that Java and Kotlin are interoperable is that all Kotlin code that targets the JVM will output bytecode that is Java compatible. And this is a big deal because it means that you can go in and you can decompile that code and you can look at exactly what it's doing. And it turns out that when we have these features like null safety, what it's doing is everywhere we have something that's not supposed to be null, we're invoking a method that says, hey, you're not supposed to be null. And you can go in and you can look at this method, and it's literally just a method that says, like, if you're null, throw an exception and clean up the stack trace so that it looks like it came from your code and not from this method that's doing the actual check. This is all that's going on. So you used to have function A, which had, like the 10 lines of logic, and now you have function B, which has the 10 lines of logic and also 5 checks that throw exceptions if something is null. And so you can imagine that that function B will likely never get faster than function A because it is doing what function A is doing, and then it is also routing through a bunch of these quick check function calls. So we're getting into this place where we're prioritizing safety over performance. Unfortunately, this is usually an okay thing to do because it's usually followed by a period of intense optimization. Now, we saw this all play out in the JVM Java example earlier with the proliferation of extremely fine-tuned garbage collecting implementations. When this was first implemented, it was very slow and very concerning to many people, but now if you go and look at GC implementations, there are so many that are tuned to your specific case that it's something that people usually don't think too hard about. Now, if you're on Android, as an Android developer like me, there's like one case, which is if you're in a hot loop that runs repeatedly very, very quickly, you may think about GC and not thrashing it, but in the vast majority of other cases, this is not something that preoccupies your daily thoughts. And we saw this exact same thing play out in the early days of Kotlin around build speed. So if you were around Kotlin, I think 5 years ago, like back when it was 0.2 release candidate, you could not mention Kotlin without someone saying, but what about those build speeds, am I right? And like, I say that, you need to just trust me on this. It was impossible to say that word. It was like summoning Beetlejuice. Like if you said Kotlin, but it wasn't even 3 times. It was like maybe 2 if you were lucky. If you said Kotlin twice, someone would pop in and be like, build speeds though, am I right? And the thing is that it's hard to believe that every conversation around Kotlin 5 years ago centered around build speeds, because today, by and large, it's mostly fine. It's not like as fast as Java, it's doing extra work, but it's not the thing that keeps us up at night anymore. And so we've seen this already play out in this language, and we're seeing it continue to play out as we're watching it now. Now, this is great. It means that like we introduce these new features and then we close the performance gap, not back to 0, but back to close enough that we don't actually really care. It doesn't usually affect us anymore. That sounds great, but the problem with this is that it's really easy to overshoot and land in this area of stagnation. And the reason for that is because when you optimize something down to the metal, it can be very, very hard to change, either due to complexity or due to the fact that no matter what you add here, even if it's a benign feature, you are going to regress your performance. And then when you add in ideas of like legacy code and the way people are currently using it right now, you find yourself in this position where it can be very hard to move out of the corner that you've been backed into. And so it brings up pretty existential language questions about like, how does Kotlin evolve? Like, where do we go and how do we keep this language from getting backed into a corner? Which is a great time to switch over to part number 3, which is where are we going from here? Now, Kotlin as a language has an ideology about how it should move forward that they've playfully termed pragmatic evolution. Now, if you were paying attention earlier, do you see what they did? Yeah? Okay. Oh my gosh, nobody saw what they did? No appreciation? Okay, well, I'll tell them, it's fine. But yeah, they're pretty into the wordplay. And they have this really, really great quote on their website that I absolutely love. This is in the developer documentation. You can go see it right now. And this is their ethos around how the language should evolve. And that is, language design is cast in stone, but the stone is reasonably soft, and with enough effort, we should be able to reshape it. And if you think about that, what they're saying is that we should approach language design questions with the utmost sincerity that they will not change. We should be confident that the thing that we introduce will be there forever. Mistakes happen, we know that. So we should also understand that there needs to be an escape hatch. We need to be able to rethink things when we've done them wrong, and given enough effort, we need to be able to go in and fix them. And so, with that, we can introduce the principles that they've come up with to help aid this mantra. The first of them is keep the language modern. Now, what this means is the language should keep evolving and we should keep condoing it. Are there any Marie Kondo? Yes, okay, I'm just getting started in this path in life. It's very exciting. There's so many things that don't spark joy. And likewise, in the Kotlin language, they have committed themselves to the very difficult work, and I can't understate how difficult it is to deprecate things that are not bringing joy anymore and to remove them. It is so much less difficult to continue to carry legacy code and not upset people than it is to go and say, you are using this, you have been a long-time Kotlin user, but this feature is not serving the language anymore, and therefore we're going to remove it, and you need to come along with us or we will drop you. That is a very difficult conversation to have, but they have committed to doing it in order to avoid this language becoming outdated and stale. So, that's principle number 1. Principle number 2 is to make updates comfortable. Now, there are a lot of ways to do this, 2 of which are the industry standards of like, give me some warning. Don't just like turn around and be like, hey, so we have like 500 changes and we would really love if you had them in by tomorrow. That doesn't fly with people, and so giving them advance notice is the easiest way to make these comfortable. But we all know that people give us advance notice all the time that we ignore, and people like will say like, hey, in a year this is happening, and then like 1 week before it happens we're like, oh shoot, in a week it's happening, better do it. And so in those cases there's this second wave, which is giving people tooling to help them out. So we'll touch on this again in the future, but for now we can move on to the final paradigm for how they believe the language should evolve, and that's to have a strong feedback loop. What this means for JetBrains is that they want to prevent mistakes before they actually happen. And so this goes back to that malleable stone analogy, where we want to commit to something, but it's pretty hard to change it. It's going to be very difficult to recast something that's already been cast in stone. So instead of going through that process, which is extremely costly, why don't we just cast it right the first time? And this is in juxtaposition, like Facebook got really famous for this software ideology of like move fast, break things, great. And I think if I had to speak on behalf of JetBrains, which should strike fear in their souls, I would posit that if they had a motto, it would be something more like, examine things thoughtfully and get it right the first time. They can use it, I give them permission. Yeah, let me know if they actually take me up on that. I highly doubt it. But anywho, together, these 3 things build up what they think the language should be as it evolves. These are their guiding milestones, and we can juxtapose those to the language principles. So, to be clear, language principles define how features should behave. So like a feature should be concise, a feature should be safe. But the evolution principles, they define how features should get introduced. Say I have a feature that is concise, safe, and pragmatic. How do I get that into the language? Those are what the evolution principles seek to address. So, how do we do this in practice? Well, there are 2 big key action items that JetBrains is undertaking. The first is making change comfortable, and like I said, there's some very low-hanging fruit on this front, which is like, give me a heads up before you drop in. And they do this with the use of compiler deprecation warnings, at least one release before they actually remove code. So this is pretty standard. And then they also do things like the very standard release system where in major releases things can break or they can change or there can be incompatibilities, and you know that those are coming because it's a major release like 1.1 or 1.2 or 1.3, so get yourself ready. But if you're just floating along in these dot releases, these minor releases, then by and large you should expect things to be compatible and you can kind of go forward with your life without being worried about being taken by surprise with any incompatibilities. So that makes it comfortable because in addition to the advanced warning, you have this expectation API where like they said, we will not spring anything tricky on you if you're in this type of release, but if you're in this type of release, you really got to check up on it because we're not making any promises. So this is like pretty industry standard. But then then there's this area that JetBrains excels at, which is providing tooling. And they've really, really committed themselves to the fact that if they decide that it is necessary to make a change that is incompatible with code that you are currently writing, they are going to do the best in their ability to create a tool to help you migrate so that you are not doing it on your own. And this is a really, really strong promise. Again, throwing back to iOS, I used to be an iOS dev, so it's what I know best. They still have an IDE where if you refactor your code, it will not find all of the use cases where that code is used, and your refactor will be left to half done. So getting tooling like this right, it sounds simple, they make it look simple, but it's far from simple. And so them making this commitment to us as users is actually astonishing, and it's obviously something that is very beneficial, because if you can have someone else do the work, of course you'll commit to doing it because you don't have to do anything. Like, that's my favorite type of work, when someone's like, will you deliver this? And I'm like, yes, John will do it. It's great. So like, them providing these tools is awesome. But then there's this second action item that they're taking in order to steward the language forward. And that's being in the feedback loop. Now, there are very, very literal interpretations of this, which is like, run a feedback survey. And they do. If you want to say in the language, they run this survey every year, so go ahead and fill it out. They ask very important things, and they listen to it. But then there are the things that are a little bit more interesting to us. Things like experimental feature flags. Now, I think that there's a lot of confusion around what experimental means, and there's actually a lot of confusion by and large. People feel this way about beta releases as well. The flag experimental does not mean that a feature is like not stable or not ready to use or buggy. What it means is that at this point in time, they have written this feature, they think that it's good, they would like to know if you think that it's good, but they are not willing to commit to 10 years of maintaining its current API until you sign off on it. And so that's what we do with experimental features. We put them out into the wild, and we say, hey, can you use this? Can you verify that our API design was correct? And if not, let us know, and we'll change it. And that's why they're under experimental flag. Not because you shouldn't be using them, but because if you find a bug, they are very open to fixing the API so that we don't live with it as legacy mistakes and regret for the next coming years. Now, there's also things like EAPs, early access programs, and these are pretty standard in the industry, but there are some niceties around what they did with Kotlin, which is that if you look at the binaries that created by Kotlin EAPs, they have this kind of ticking time bomb where they actually usually make them incompatible outside of the EAP period, which means that if you pull this early access code and you're using it and you find a bug, then when they fix that bug and they create the actual preview that you're going to use, the stable release, then they'll make it so your old binary is no longer compatible, so that the bugs found during this phase do not live on. You don't have some preview release and it has a bug and you write it and now you're using it for 5 years and these bugs are getting filed against the tracker saying hey, in this one preview release there was this bug. They kind of make it so that you have to push yourself forward so that these bugs don't continue to live. So that's pretty cool. And then we get to the fun one, which is that Kotlin was open sourced extremely early on. I believe that development on it started in 2010, and then we got our first look at it as public in 2011, and you can compare this to Swift's evolution, which also I believe started in 2010, and then did not go public until, 5 years ago, I guess now? So far after Kotlin had shown itself to the public. And so they have a very strong commitment to having this language be open source. And the really pertinent part about it being open source and about where we're going next is that you can visit GitHub. Hooray! And this is actually really, really cool. I joke about it, but the future of the language is documented in an open source repository. These are called keeps. Proposals for when the language or where the language should go, new features for it, are called keeps, which is the Kotlin evolution and enhancement process. And you can just put in a pull request where you define what you think should be added to the language, and you give a very detailed and thought out rationale why, and people can debate validate this, and you can see all of this playing out on the repo right now if you want to go and look at it. So like the future of the language is out here for all of us to evaluate. These are snapshotted. I think I took this as of like 2 days ago or something. So these are all up-to-date things that the language is currently considering bringing in, and you can see like some of them are contentious. They have 84 comments. Some of them people are just ignoring, but you can see this process play out in real time. You can have these conversations with the people actually implementing that. But as with any PR, there has to be someone at the end who decides to actually merge it, who decides like, yes, you made a proposal, we're going to accept it. So who is actually doing this work? Well, it turns out that as of, I think 2 years ago, the Kotlin Foundation was formed. I believe it's 2 years, it might be a little bit more than that. But anywho, there is a Kotlin Foundation. And this foundation has like 2 key points, which is one, it has a lead language designer. And the lead language designer sounds like a miserable job because you're on the hook for everything. Like, you are the end-all be-all for this language. That sounds like a lot of weight. I feel like I have an ulcer, so I'm glad it's not me. But they are not entirely alone in that they also have like a language committee that they can share blame with. And the language committee, their charter is not, they are not where the buck stops for the language design. They are where the buck stops for how comfortable updates are. So they are this checks and balance feature saying, okay, you want to change the language in this incompatible way. We are going to vet that this will be a comfortable update and that you've made all possible attempts to provide tooling, to provide documentation, and to make it easy. And when you stop and think about that, like this is a direct quote on what their job is. We literally have oversight. There's only 2 roles, and one of those roles is to make updates comfortable. I think that's really cool. I mean, that's pretty wild. Like there's 2 things, and half of them are dedicated to our comfort. Now, if you look at the people behind these roles, the lead language designer is Andre. It has been since the beginning of Kotlin. If we are all very lucky, it will be for the next 100 years. Like if someone figures out how to extend human life, he should be our first candidate. He's incredibly thoughtful, and I admire his like logical skills and the way he interacts with the community greatly. But then there's also the language committee, and he also serves on the language committee. And this is a thing that I can say because I don't work at any of these companies. You can notice like the fun politics that are playing out here. So obviously like Android is using Kotlin now, which is great, but that was like really risky for them to depend on a language that some other company owned. So they did this thing where they moved it into Foundation, but then JetBrains still has this claim to fame over like, we created Kotlin. So you can see that it's very carefully balanced of like one JetBrains representative, and then one Google representative, and then like one third-party observer to break up the fights, or like, you know, don't tell them I said that, don't tell them I said that. But like one like neutral person. I think that William works at UT. I might be wrong about that, but I met him once. He's a very nice person. And there's like this one tie break. So I love this. It's like me gossiping over in the water cooler. It's great. But anywho, there's no good transition to my last property, which is part 4. What's old is new again. And so at the start of this talk, I started with this idea of like the JVM was so cool because you could write code once and then you could run it everywhere. And again, like that looked something like this, like one input everywhere. Great, magic. And then you fast forward about 25 years and you realize that like VMs aren't for all use cases. Like you can't use them everywhere. Like embedded systems are like things controlled by Apple. iOS. Anyone? Yeah. So like VMs don't always work for people. And so when you look at the future of the language and you look at where resources are being allocated, there are efforts like Kotlin native that are taking up significant bandwidth. And what does Kotlin native look like? Well, I'm glad you asked. So like there's the JVM situation over on the left-hand side of the screen. And then there's the Kotlin native on the right-hand side, and it's wild because it almost looks like we're doing exactly what we started with 25 years ago, which is creating separate binaries for all of these different platforms. The difference, of course, is that before, you would be expected to create all of these separate binaries to target all of these different platforms, and now Kotlin native is going to do the work for you, so that's cool. But you can see that we're really kind of going in like, not circles, because that implies that we're not making forward progress, but we're revisiting concepts from places where we began. And when you do things like this, when you revisit these and you start doing these platform-specific implementations again, you run into questions about things like concurrency, or, I kid you not, memory management. I had to put it up here. We started here, I had to end with it. A small note on this, they actually already have a memory management model. It blends like automatic reference counting with cyclic garbage detection. So they have actually decided on this, but the fact that they had to decide on memory management when it all started back in the day with garbage collection, I thought was just like perfect. And all of this is just to wrap up and say that while the future of Kotlin is expansive and exciting and seems limitless, we're not in the journey alone. We're kind of like standing on the shoulders of greatness, and for better or worse, whatever you feel about Java, it remains to this day, 25 years almost later, one of the most popular languages in the world, and that is an impressive feat. So us as Kotlin enthusiasts, when we look at our history and we look at where we're going and we realize how much we owe to this technology, that's a great place to be because we're standing on the shoulders of giants. So with that, I hope this walk down memory lane inspires you and makes you excited about Kotlin, because there's a great day of presentations in the next couple hours, and that's all I've got for you. So thank you for listening to me, and I'll see you all around the conference.